Welcome everyone. It is my great pleasure to welcome you here to Bundle Adjustment Part 2. Today we want to look into the numerics of bundle adjustment. So I assumed you've attended the first part of the bundle adjustment lecture, and now we want to look into the numerical tricks that we can apply in order to solve the system of linear equations that I need to solve in the context of the least squares error minimization that happens during the bundle adjustment problem. Before we want to dive into those numerics, just give me 3 to 4 minutes to rehearse what I talked about in the previous lecture on bundle adjustment, so that we are all on the same place. So bundle adjustment happens, for example, if I fly with a UAV over an environment, I take images and I want to build a map of the environment indicated here. So these are the different image planes virtually displayed over the ground, and what you see on the ground, this point cloud, are 3D points with their 3D locations computed from those images. And that's exactly the problem that we are tackling here. So you can also have this in kind of more illustration form. These are the different locations of the aircraft or the UAV on the ground, and you have certain points on the ground that you're seeing, observing from multiple camera images, as well as some of those control points for which you assume to know the 3D coordinates. And the question is now, how can we determine the locations of the camera as well as the locations of the points in the world? So a 3 degree of freedom vector we need to fill for every point in the world, and a 6 degree of freedom vector for every camera, taking into account its position and orientation, maybe even more parameters if we take calibration parameters into account as well. And so what the bundle adjustment problem does, it tries to solve this task in a least squares fashion. That means we are setting up a least squares problem, which leads us to a system of linear equations that we need to solve. And this provides us with a new estimate of our camera orientations and our point coordinates. And as is a nonlinear problem, it's something that we need to iterate. So the key idea is we start with an initial guess, and then we take the 3D points in the world in our current estimate and project them into the images, or where we think the cameras are, and compute basically a virtual image, so to say. And then we basically minimize the error between the actual image and this virtual image, or at least the reprojection error. So where is a point reprojected to in my virtual image, and where is the point actually measured? And this discrepancy is what I'm trying to minimize in a least squares fashion. So we can actually set that up in the following form. We have here the coordinates of a point in an image. So ij, I is the index of the point, j is the index of the image. So this is the 2D pixel location of a point in an image. Then we have our corrections applied to it. And then here on the right-hand side of the equation, we have a scale parameter resulting from the fact that we are living in a homogeneous world over here. So every equality is only defined up to a scale factor. And then what we have over here is the 3D coordinate of the point in the world, so point I, and the projection matrix of camera J that projects the point I in camera image J to the image plane. And this matrix involves a couple of nonlinear parameters, the nonlinear calibration parameters, as well as the orientation parameters that need to be taken into account over here. So we have scale factor, our projection matrix, our 3D point, and the projection matrix has several parameters. So these are the projection parameters, so the extrinsics and the intrinsics, as well as some, let's say, nonlinear distortion parameters that I need to take into account. And this may be even pixel dependent. So depending where a point is projected to in the image, I need to apply a different correction. And this all happens under an uncertainty in the image coordinates. So this is the assumption, how precisely can I pin down the points in my image? And what this equation actually does, it assumes known data association, something that may not be directly clear if you see that for the first time, but given that is the point I is given over here, so the index of the point I, and I have the index of this point I in the image as well, and I assume to have all the IDs of the images of the point in the image and the point in the real world. That means I have a known data association, so I know which point is projected to which pixel location, and there's no ambiguity in the data association. And so our unknowns that we need to tackle in here are the coordinates of our 3D points in the world, so our new points, the points which are not control points. we have the scale factor, which happens for every point and every camera image. So the huge number of those parameters over here. That we have the 6 degree of freedom exterior orientation, 5 degree of freedom interior orientation, plus some nonlinear parameters. And so this can lead to a potentially large number of parameters, and especially the problem is the scale factor over here. This is the factor which occurs most often, and is actually a parameter I'm not really interested anymore, because this factor doesn't tell me anything in my Euclidean world, because it's only something that exists because I'm operating in homogeneous coordinates. And as a result of this is one of the few cases where it makes sense to go back from the homogeneous world into the Euclidean world and do this minimization in Euclidean parameters. And I can actually achieve this by taking the last row of this vector matrix multiplication, which is the homogeneous normalization. So I take the first 2 rows and divide it by the 3rd row. This is then the Euclidean normalization, so going back from the homogeneous world into the Euclidean world. And as a result of this, everything happens in the Euclidean world. And in the example that we had discussed last time in the lecture, this helped us to go down from 13 million unknowns to 3 million unknowns, just as an example. And if I now have this equation, then I can use my standard least squares approach, the standard procedure that we know. So we have our unknowns and our observations. We set up our normal equation system. So the coefficient matrix or Jacobian matrix A, this is the covariance matrix or the inverse of it, so the information matrix, my unknowns, and here my observations. And this leads me to the update of my parameters, of my unknowns over here, given this form, and this is basically what I need to do. And in order to solve this system of linear equations, I need to solve this least squares problem, I need to solve the system of linear equations, and the problem with this is that this can be a large system, as we have seen last time. And this brings us to the question, how can I actually solve this? And this is where this lecture basically starts, the part 2 of the bundle adjustment lecture, looking to the numerics of the bundle adjustment problem. So why is it challenging to solve such a system, and what information or what facts can we actually exploit when solving the system in order to do this in an efficient manner? So what we have seen also last in an example, but I can actually repeat that in a second. We cannot solve the system of linear equation in a straightforward manner that pops out of bundle adjustment problems of a typical size. Why is this the case? The reason for this is that the resulting systems are huge. So we have a large number of unknown parameters and a large number of observations, and the number is typically too big in order to solve this at least in a reasonable amount of time on my standard computer if I don't use any tricks. So just as a kind of small example how that could look like. So assume we have 20,000 images that we have recorded. We have 18 points per image, so it's a rather small number of points compared to what today's typical image feature extractors such as SIF features would produce. And we assume that we see every point 3 times. So we have 3 observations per point. So every point pops up on average 3 times in an image. So this means we have 120,000 points overall for which we want to estimate their 3D location. So 120,000 multiplied by 3, because it's an x, y, z coordinate, gives us 360,000 location parameters. We also have camera orientations. We have 20,000 camera images. Every camera has an exterior orientation which has 3 degrees of freedom, so x, y, z, yaw, pitch, roll, which gives us 120,000 orientation parameters. 360 plus 120 gives us 480,000 parameters, and we have 720,000 observations because we have 20,000 images and we observe every point 3 times and have 18 points per image, and we observe an x and y coordinate. This gives us 720,000 observations. Note that in this calculation I excluded the intrinsics, so the calibration parameters, because the number is typically small. It's something maybe around 10 that you may want to take into account, so it doesn't really play a role in here. So we have roughly 500,000 unknown parameters and roughly 750,000 observation. This will lead to a Jacobian matrix which has 3.5 times 10 to the power of 11 entries, and even the normal equation has 2.3 times 10 to the power of 11 entries. And that's huge. So if you assume that you have, let's say, double values, then even storing the Jacobian leads to something like 2.8 terabyte just storing the entries of this single matrix, not even having done anything with it. And 2.8 terabytes is a huge number. That's maybe something that your computer can store on its hard drive or maybe even in memory, although that's very unlikely. You see that this is a big number. It's probably too huge to solve this in a reasonable amount of time. So we need to think about how can we actually do this? How can we exploit certain properties that the bundle adjustment system has in order to lower those numbers down? So this is too big to be solved in practice for practical applications. So what can we do? In order to understand the underlying structure of the bundle adjustment system, let's see how we typically acquire image. And we start here with the acquisition of images from an aerial vehicle, but very similar facts also hold if you just take a camera and walk around a scene and record a scene. The structure is slightly more simplified here, so it's very easy to illustrate the matrices and the entries of the resulting matrices if we start with these equations. Therefore, I'm doing this, but similar structures, not as symmetric, but in a similar way, will also occur if you just take your camera, walk around a scene and record images from the scene, for example, or drive as a vehicle through the cities and record images and want to build a 3D reconstruction of those images. So not much changes in this sense if you don't have that flight pattern. But the flight pattern helps us to understand the structure probably pretty good. So again, this is the example that we used in the end of the previous lecture on bundle adjustment. We have a UAV that flies over the ground. There are 7 times 7, so 49 points, of which 4 points, those in the corners, are control points, for which I know the orientation. All the other points are new points. And I'm basically flying in kind of 3 stripes over the scene, recording 7 images per stripe. So 3 times 7, 21 images. So the first image over here covers 6 points, 1, 2, 8, 9, 15, and 16. So those points, and then I'm basically shifting by 1 point the images over the scene until the last image I take has the points 6, 7, 13, 14, 20, 21. And then the airplane goes down and records those images over here. And that's basically how I obtain my image. So I have 3 stripes, 7 images per stripe. This is here an overlap of 60-20, so a comparably small overlap for UAV mapping if you want to generate high precision maps. This means we have 21 images, 49 points, of which 4 are full control points. These are those points in the corners where I assume to know the x, y, z coordinate, so known point coordinates. And that means we have 45 new points. These are all the other points in here for which we have to estimate the 3D location of those points in the image. And so that's the underlying estimation problem. These are the images that we have, and we want to exploit this this structure and illustrate the resulting matrices, such as the Jacobian matrix or the normal matrix, based on this example over here. So what do we have? We have 6 images with 6 points. So this is this image, the last image, the one down here, basically all images on the side. So image 1, image 7, image 8, and so on and so forth. They have 6 points per image, and all the other images have 9 points per image. So 6 times 6 and 15 times 9 points. That means we have 171 image points, and we have 2 observations per image point. So there's a 1 missing, sorry for that, a copy-paste mistake. So 2 times 171 gives me 342 observations, and of which my unknowns are 45 points that are unknown points with 3 parameters each, x, y, z, gives me 135 unknowns, and for the orientation parameters 6 times 21, because of 21 images, gives me 126 unknowns. So in sum we have 261 unknown parameters and 342 observations. So this is kind of a much smaller problem, and this is something that we can actually still illustrate and look how the structures of the underlying matrices look like if I build up this linear system for this example. In order to make that even a little bit easier, we kind of change, or we rearrange our variables now a bit. Okay, we do the following. We start with saying we have our observations, our corrections, and then we have our Jacobian matrix and our delta x. Okay, so what we can do is we now look into this vector x, and the only thing we are doing, we are rearranging the order of the variables in there. So we could say first we put the orientation of the first camera image, then the points that we see, then the next camera image, and then the points that we see. That would probably be the natural way how you would do that if you implement it on your own. What we now want to do is want to kind of separate the location of the 3D points and the 60 orientation parameters. So we put all points coordinate first in my vector. These are these delta k. These are the coordinates of the points. And we have the delta t, which is not a translation vector here, t, but this should be a 60 vector for every camera, so the camera orientation parameters. So the only thing I'm doing now, I'm kind of rearranging the variables in my vectors that first I have all the 3D locations of the points, and then all 60 orientations of my camera. So x, y, z of the first point, then x, y, z of the second point, x, y, z of the first point, and so on and so forth. And then x, y, z yaw pitch roll of the first camera, x, y, z yaw pitch roll of the second camera, and so on and so forth. So this is kind of the reordering of the variables that I'm doing in my unknown vector delta x. Okay? So if I then write down my equation with my matrix A, so delta L plus my corrections, is this matrix A times delta x. And now I know that delta x consists of a delta k and a delta t block. This means what I can do, I can take my matrix A and basically cut this matrix, not exactly in the middle, but exactly at the point after 3 times delta size of delta k. I made a cut in here, and that would then give me 2 matrices, a matrix C and a matrix B. Okay, so it's just kind of splitting our matrix A into 2 matrices, a matrix C and a matrix B, having the same entries. Okay, so if I then multiply this matrix with this vector, as a result, the matrix C will be multiplied with the delta k, so the point parameters, and the matrix B will be multiplied with the orientation parameters, so that I have C times delta k plus B times delta t. Okay, so this is just from the reordering of the vector. I can say these matrix A consist of 2 parts, and they probably have a different structure because one is related to the 3D point coordinate parameters and the other one is related to the 6 degree of freedom orientation parameters of my camera. Right? So this matrix C and this matrix B will probably reveal a different structure. What we're going to do, we are going to investigate the structure of these matrices B, C, and as a result of this also A. Okay, so what do we have? So this is just basically copy-paste from the previous slide. We have our C, B, with our matrix A, times K, T, which is our X vector, gives me this form. That means we have the same thing for all the individual observations. So for every point observation in every image, we actually get this equation. And it has 2 parameters. So because it's a 2-dimensional observation, I'm observing the X coordinate and the Y coordinate of a point in an image. So for every observation, ij, so I is the 3D point that I'm observing and j is the camera image. So for example, point 15 in camera image number 3 gives you a 2-dimensional vector of the observed x and y coordinate. So as a result of this, this matrix A transposed ji is a 2 by u matrix because it's 2-dimensional, and this is the unknowns that I have. So that means the Cij is a 2 by 3 matrix, which is multiplied with my orientation parameters, because they are 3-dimensional. The output must be 2-dimensional, so this must be a 2 by 3 matrix. And similar here, the output must be a 2-dimensional matrix, and this is 6-dimensional, so B must be a 2 by 6 matrix, or B transpose must be a 2 by 6 matrix. Okay, so I know that these are kind of small blocks that I'm actually having here. And the coefficient matrix will be filled with those matrices. And the key thing, and that's kind of an important part in here, is that this matrix is 2 times u. So this is all the number of unknown that we have, because this is this high-dimensional unknown vector. But I know that only a small number of the parameters will actually impact what I'm going to observe. Namely, for estimating where point whatever 10 is seen in image number 2, all the other camera image locations don't matter and all the other point coordinates don't matter, right? So it's only the coordinate of the point itself and the orientation of the camera which observes that point. So this means this U, and U can be very large. These are all my unknowns. In my example before, this would be a 240,000 dimensional vector or matrix over here. So 2 times 480,000. I know that the result will only depend on a 2 by 3 matrix C that maps exactly those parameters of the point K I'm actually seeing, and a 2 by 6 matrix B, which relates that to the location of my camera and the orientation of my camera. So this is basically the camera image J and the point I. All the other points don't matter. So the important thing to note that, of course, this matrix C and this matrix B will be different for every point and every camera image. But it means that the majority of those entries here don't matter and thus must be 0. Right? So this is a very, very important point. Probably the most important point of this lecture here today is this insight that only the point I'm observing and the camera which I'm observing the point tell me something where this point will be mapped to. All other points, all other camera locations do not matter for that computations, thus have no impact, thus must have a 0 coefficient. And again, this coefficient matrix is the Jacobian of my error function, and there also becomes clear if you have a parameter that is not involved in the estimation, derived with respect to that parameter, that entry will be 0. And that's the reason why the Jacobian or the coefficient matrix here has all those zeros in there. So our matrix has this structure over here. So this is basically these submatrices, how the different points are seen. And this leads us to matrix. If we expand one of those matrices, of these IJ matrices, will be matrix which will be basically have always zeros just at the right location where the mapping goes to the point I and the camera image J. There sits this matrix C transposed. The rest is 0 again. And in the B block, exactly the same happens. Everything is 0 except this single block, which is related to the camera that actually observes that point, to the camera J that observes the point I. So as a result of this matrix has these individual rows, and those rows are basically 0 for nearly everywhere, and just a small number of points remain. So the key insight in here is we have a sparse matrix. A matrix where the majority of entries will be 0, and we just have small blocks in this matrix where the blocks are non-zero. So when I was talking about a row over here, of course the row is not really the correct word because it is it's a 2-dimensional row, right? So these are 2 dimensions. So these are vectors of dimension 2. And this is a 2 by 3 matrix, and this is a 2 by 6 matrix. So there's, in every row, there are basically, if you take it to a real row, it would be 3 plus 6, so 9 non-zero entries, and 9 non-zero entries, and the rest would be 0. And I have that basically twice, once for the x coordinate and one for the y coordinate of my observation. Nevertheless, the key insight, this matrix is sparse and has mainly non-zero elements. And you can see this, the result for that is because basically not in every camera image you observe every point. If you would observe in every image every point over all images, then this matrix would be more densely filled with values, right? So that's kind of a key thing, but that's not the case in realistic setups. In realistic setups, we move through the world, we move our camera through the world, and we're observing new points. We are not observing the same scene all the time. And as a result of this, in reality, this matrix is sparse. And this matrix has actually a very, very clear structure. So if this is my full matrix A broken up into the matrix C and the matrix B, here I have the number of observations, and here I have the number of points and the number of images that I have, right? So these are all the points that I have, and these are all the camera images that I have, and these are all the observations that I have. This is the structure of the matrix A. And what you can definitely see a certain pattern over here. And this pattern is so symmetric because of my flight pattern. So this basically is a block that corresponds to the first stripe. The second block here is a block that corresponds to the second stripe, and the third block over here is the one that corresponds to the third stripe. And we can see certain properties in those matrices. So if we make basically a cut through this matrix, we take one row or one block in those matrices out, those different blocks tell me something. So the non-zero elements, non-zero blocks that I have in here, basically gives me the number of times a point is observed, right? So these are my observations, these are my points. So if I go down and count the non-zero elements, it basically tells me how often has a point been observed by camera images. And again, this is 0 most of the time, just a small number of times a point is observed with a camera image. And a similar effect we can see here. If we basically make a cut here through this matrix, then here again we have the number of images, we have the number of observations. So this tells me basically how many observations do I have per image? How many points do I see in that image? So if this is image number 1, 2, 3, 4, 5, 6. This would be the 6th image. How many points do I observe in here? You can also see here that this block, the 1st, the 7th, the 8th, and so on, are smaller than the others. The reason for this is because these were the points, images at the beginning and the end of a stripe, where I only observed 6 points instead of 8 points. And therefore, you can see that those guys are a little bit smaller than the other elements in here, because they are 3 points less that are observed. So if I cut through this matrix here, this basically gives me number of observations per image, so the number of points that I see with an x and y coordinate. And if I make the cut here, it gives me the number of times a point is observed overall. So it's a structure, this matrix has a structure which is related to the measurement process. So depending how I record my data, this matrix will look different. And I want to now dive a little bit further investigating the submatrices Cij and Bij that I want to look into. So the matrix C, starting with this one over here, consists of this 2x3 submatrices Cij transposed, which are those matrices over here. And this is basically the connection that we have of a point that we observe in an image. So Xij prime, this is the x, y pixel location of the point in the image, with the actual point that I'm observing. So because this is the point itself, and this is the observation. So it connects the points and the 3D points in the world and the observations in the image with each other. And we only have per row in this matrix C one non-zero 2x3 matrix per row. So row is basically a row of size 2 because one for the x coordinate, one for the y coordinate. And as you have seen, this what I've shown in the beginning for motivating this sparsity constraint is that we only have one element, one Cij transposed, which sits in one of those rows. So to one of those rows, I have only one 2x3 block, and the rest is 0. And the number of non-zero 2x3 matrices per column, this was kind of the column that I've shown before, tells us how often the point or a point xi has been observed in the overall mapping process. So maybe the point would kind of show up here again. That means the airplane would have taken a second round and is doing the mapping again, or closes the loop and goes back to the beginning. Then we would have additional points showing up over here because the point would have been observed another time down here. And this is what we can see from this submatrix C. We can also investigate the properties of this matrix B over here in a very similar way. So this is the second part of the matrix. This was the one relating the camera image and the number of observations. So basically looking how many points I'm actually observing in the individual camera images. So it consists of this 2x6 matrices relating the camera orientation of the camera J with the corresponding observations. So it links the observed point Xij and the J's camera orientation. So where is the camera? If I change the camera, of course, this has an impact on where the point will be projected to in my 2D image. And again, we have one non-zero 2x6 matrix in every row. So if I go through a full row of the matrix, I will have one 2x3 blocks Cij transposed and one 2x6 blocks Bij transposed. So basically every row has 9 non-zero elements, either one-dimensional or two-dimensional, if you only take into account the x or y coordinate, of course. So the number of the 2x6 matrices which are non-zero per column, this was the cut that we have done over here, basically tells us how many observations we have in an image, so how many points I'm actually observing. Okay, so another question is, how do these Bij and Cij actually look like? So if you go back to the photogrammetry 1 course on the projective 3-point algorithm, we actually did some derivations in there, and we have seen that for the normal case, so this is an important setup here, it only holds for the normal case if the camera sits in the normal case, then this would be the resulting elements of your matrix. So the normal case is a special case, and it only holds for that normal case. So if your camera is in a certain location that is specified through the normal case. For the general case, and that's what you would need to do if you want to implement that system, those guys don't help you because your cameras are never always in the normal case. You want to optimize your camera orientations. The problem then is for the general case, that becomes more tricky. Actually, you can still derive it by hand, but it's more demanding. You will write down several pages full of derivations, so that's something that you will for sure make mistakes. In practice is a very demanding and daunting procedure. And therefore, in practice, we always use mathematical toolboxes which actually do those computations for us. So there are two common ways. Once you compute your Jacobians analytically, this is kind of the standard approach. There are toolboxes out there where you can specify the equations. So that means how your point is mapped through the projection matrix into the camera image, and you compute the first derivatives, all the partial derivatives of this, which forms your Jacobian, and it basically generates automatically code that you can put into your whatever C or C++ program, and you get the computations out automatically to avoid the mistakes that you're doing while typing those equations down. So this is then specific for your implementation. Another alternative, which also becomes more popular over the recent years, is actually compute the Jacobians numerically. We don't have to do those derivations then by hand or put them in via a program. There are toolboxes or solvers out there which actually compute the Jacobians numerically. That is also possible, but kind of the way I would commit to here for that lecture would definitely be the way for computing them analytically. That means we write down our equation and use our toolbox, say compute the first derivative with respect to all the unknown parameters, and then you will automatically get code generated which does this for you. So we don't specify them here manually because they would fill several slides for the derivations if you would need to do that by hand. So I assume we have a way for obtaining these Cijs and the Bij matrices over here. So once we have specified that, so once we have our Bij and Cij matrices, the next thing is, how do we build up our normal matrix for our normal equation system? So again, the important insight in here that this is a matrix which is sparse. Why is this the case? Because our Jacobians are sparse. So this was my A matrix, and I'm turning into my normal matrix by computing A transposed, the uncertainty of my observations inverted, so the information matrix of my observations, and my Jacobian as well. And so this will give me a matrix in the dimensions of the unknowns that I have, so number of unknowns, which will have this form. And again, through the arrangement of my unknown vector into 3D points followed by orientation parameters of the camera, we can also see a certain pattern showing up here. So this matrix consists of 4 blocks. So these blocks, they are the same blocks, okay, swapped of course, and then we have the matrix blocks here, which are the interesting parts as well. This is the one relating the camera the point orientation. So these are all 3 by 3 blocks. So this is basically diagonal block matrix, which contains of 3 by 3 blocks in this information matrix. Okay, and this matrix down here, this normal equation matrix, is a matrix consisting of 6 by 6 blocks. So all the camera orientation, 6 by 6 parameters, are specified down here. And these off-diagonal elements basically link the camera orientations with the points that are observing. So this basically tells me which points are observed in which camera image. So you can still see the structure over here, which tells you what has been seen, which camera orientation is linked with which point parameter. And this matrix is still a sparse matrix. So those matrices are clearly sparse. They only have the block diagonal elements, and those matrices are still sparse. They are less sparse than those elements, and they basically encode how often, so how the camera was moved through the environment. If you're observing the same scene over and over again, or more and more often, these matrices get more densely packed with non-zero elements. If you just walk through the environment, for example, once, and you have only a very limited field of view, then this matrix will get sparser and sparser because you're only relating the point that you see with the camera images. And if you're observing always something new, or more or less always something new, then those matrices will stay more or less empty. We can look to the same example if we kind of increase our problem. Let's say we have 7 stripes with 15 images per stripe, so we just scale up the environment that we are covering. Then this would be the resulting A matrix, Jacobian matrix that we have. We can see exactly the same structure, again, that we have now more stripes and more images per stripe. And if we then compute A transpose A times the weight matrix, then we would get this structure. And we can see that the number of non-zero elements is actually increasing over here because the matrices get larger. They have mainly non-zero elements, so the number of cells, elements that we have is basically quadratic, and the number of fillings that I do is kind of linear. So the larger the number the matrix gets, with this under the same movement pattern, so to say, the more zero elements I actually get in there. And so if we kind of just make a few computations for this simple problem, we have in the A matrix 3.3% of the cells which are non-zero, and they're more for the N matrix, because smaller, because it only depends on the number of unknowns and the number of observations are not in there. And if I go for the larger matrix, those numbers decrease. So the larger the matrix is, the more sparse it actually gets. So it basically grows linearly with increasing the camera images and the points that I'm seeing. The kind of fill-in in this matrix is basically linearly increasing, although the elements I have in my matrix is quadratically increasing. So there will be more and more zero elements compared to the non-zero elements. Okay? So let's have a look to this normal matrix. How does this normal matrix look like? And maybe we can exploit, besides that it is a sparse matrix, so we should use sparse solvers to solve it. Maybe we can even do a bit more and see what kind of structure we can actually exploit. So we assume that we have a block diagonal matrix for our observations. That means I have a covariance matrix in my image, a 2x2 covariance matrix, but the individual point observations are independent from each other. So the every 2x2 block can have off-diagonal elements, but basically it's a block diagonal matrix, so there's no correlation between different point observations. So that's basically the assumption that I have in here. In this case, my normal matrix, which is A transposed, information matrix A, I can set up A or split up A in C and B. So A transpose gives C transpose B transpose and CB here for A. And then I can multiply those elements out. So I will have here blocks relating C, the observations, B with the observations, and so on and so forth. So I basically have my normal equation system with those elements NKK, NKT, NTK, NTT, and these are those elements that we have discussed before. So this was kind of the example that we had down here, and you can see NKK is this matrix over here, which corresponds to this block, NTT, this block over here, and those correspond to the off-diagonal blocks over here. Just this one is just the other one transposed. So what do we have? This over here, this NKK, is a block diagonal matrix with 3x3 blocks on the main diagonal, the rest is 0. Similar, NTT is a block diagonal matrix with 6x6 blocks encoding the camera orientation parameters. And these matrix over here consists of several 3x6 blocks, and these are the connections between the points that I'm observing and the camera from which I'm actually observing these points over here. So all those elements in this matrix can be computed very easily. So on the off-diagonal elements down here, I simply compute C, sigma I, B transposed, and the others are my diagonal matrices, where I'm just kind of collecting the observations of all points, all images where the point I has been observed gives me this sum, and all the points that are observed in image J, I'm summing over those points, compute those entries. So I can directly compute all the elements of my normal matrix directly from my small low-dimensional matrices Cij and Bij. So I can fill those numbers here directly and don't have to build up the matrix. I can just store, for example, or directly compute all those non-zero values. Again, if I'm using modern toolboxes for sparse matrices, I can actually allocate a large matrix and fill those matrices. So then this is automatically taken care of from the sparse matrix library that you're using, but you can compute all those elements explicitly, individually, if you want to store them individually on your own, for example. Okay, so let's see what else we can do, given the fact that we have split up our unknowns vector in the number of, in the 3 point coordinates and the camera orientation parameters. How can we actually exploit that further? So we have our normal equation matrix n delta x equals h, my right-hand side, and I know that this n had this structure that I was exploiting before. I know that x has the structure k and t, and I'm kind of not splitting up my right-hand side, just making hk and ht over here without specifying at the moment further. So this is kind of the structure that we have in our normal system equation. And now I'm doing a trick. And this is a trick which may be unintuitive at first, but it's kind of an informed tip. So I tell you that we can do manipulation to this equation now, which then will simplify our life. So we just do a manipulation now, and then later on see that it actually simplifies my life. And what I'm doing, I'm multiplying both sides of the equation with another matrix from the left-hand side. So I'm multiplying a matrix over here and I'm multiplying a matrix in over here. A matrix that I specify, a matrix that you don't come up on your own that easily, but a matrix, if we use it, it'll actually simplify our computations. And this is this matrix over here. So this matrix contains elements that stem from this normal equation matrix. And I'm doing this because I want to bring this matrix here, which sits in front of the delta x, into a special form. So what do we have in here? We have the inverse of the nkk block. The inverse of the nkk block pops up here again, and we have the ntk block over here, and this is an identity matrix. So I'm taking this matrix over here and taking this matrix over here, and I'm multiplying both equations with the same matrix from the left-hand side. So I'm not changing the equation itself. The equation is still the same. And what I'm then doing, I'm just doing this matrix multiplication over here. So whatever, I'm taking this vector, multiplying it with this vector gives me the first element, then this multiplied with this multiplied with this one, this multiplied with this one, gives me my 4 elements that I have in here. So for example, this multiplication over here is nkk inverse times nkk plus 0 times this matrix gives nkk inverse times nkk gives me the identity matrix. And I'm doing the same for all the other blocks. So I'm ending up with a 0 over here and these equations over here, right? So and now an interesting thing pops up. And the interesting thing over here is that I have this 0 element, this 0 over here. So this part over here is 0. So what I can do now, I can just take out the lower block over here and solve this lower block, because if I multiply this vector with the unknown, this vector here with this unknown vector, all the delta k's will go to 0. So I'm only what I can do is I can solve only for the unknown parameters delta t. So I'm just basically cutting out that system over here, and then I'm only solving this part. So ntt bar, so this is my ntt bar, so this is the matrix n bar, and I'm taking out the tt block, so ntt is this one over here, times delta t equals h bar t, and this is just the definition of my h bar t vector. Okay? So if I kind of look to my matrix n, I can turn this into the matrix n bar tt, which is this matrix over here, which gets smaller, but it's more densely filled. And okay, this part I'm ignoring for now. I can do the same, could do the same thing for the other matrix over here. But this reduced system here, matrix is still sparse. And in our case, it's a 126 by 126 dimensional matrix, because this has been the involved parameters that we have in here, orientation parameters. So the number of unknowns that we have from our 21 images, 21 images with 6 parameters. So 21 times 6 gives me 126. And therefore, this is a 126 by 126 matrix. Because if we solve this system, this one over here, we are basically computing our orientation parameters from our camera, ignoring the point parameters. Okay? So what we can do Okay, we can first illustrate this. So this was the original matrix. We computed the normal matrix out of this, and then actually this reduced normal matrix for NTT only. And you can still see it's still a sparse structure. It's more filled than this entity, so you get this off-diagonal blocks over here, but you're kind of still remaining a sparse matrix. And the larger your matrix is, the sparser this matrix still gets. So let's have a look to this matrix, because how difficult is it actually to compute this matrix in here and then actually to solve it. So what we can see in here, in order to compute NTT, we just need elements from the matrix N and only 2 blocks that we need here, which requires a matrix inversion. So for computing this, we need to invert the NKK block over here. But the good news is that this is an operation which can be easily done. Why is this the case? The reason again is because we know it's a sparse block diagonal matrix. So we know that this block NKK by design is a block diagonal matrix where the blocks are always of 3 by 3. So the only thing we need to do is we need to invert those individual blocks down here in order to compute the inverse, which is much easier than inverting a dense matrix. So this is something that can be done easily, basically in linear time, in the number of points that I have. So it's an operation which is linear in the number of points for computing this inverse. So that means I have my matrix over here, my n bar TT, which I can compute. And what I'm doing, I'm just solving this matrix, still using a sparse solver. So a matrix which supports sparse matrices and allows me to solve them quickly. So I have this matrix N, which is not only the number of unknowns, a squared matrix, the number of unknowns, as a sparse matrix, which I need to solve. And if I solve this matrix, I solve it for T, so I obtain my camera orientation parameters. I know where the cameras are after doing this trick. And I can do this in an efficient manner because this matrix here, this NKK matrix, is this block diagonal matrix. If this matrix would be dense, this would be a very costly operation to already set up this matrix, and it wouldn't be of any help. So after I've done this, I kind of completed the first step of my estimation problem, namely that I have computed the orientation parameters of my camera. Now what I need to do, I need to compute the parameters of my 3D points, exploiting that I know my camera parameters. So I want to obtain the 3D points given this delta t, given that I computed it. And this now can be easily done. I still have the system that we had over here, where we kind of cut out this lower part and solve this lower part separately. And we solved this for delta t, so delta t is known now. So what we can now use is we can solve for the first part and directly exploit that we know delta t. So we take this, we multiply this vector here, or this matrix, with this vector. So I times delta k plus minus nkk inverse nk delta t gives me this part of the equation, nkk inverse hk. So this basically gives me this equation down here. So multiplying this one with this element equals this element. So this is what I can extract out of this. And this is now an equation which contains the parameters k, and it involves the delta t that I computed in the previous step. So I can only do this because I was able before to solve delta t separately without knowing k. Okay? So what I then do, I kind of move this to the other side, and so that the resulting equation returns into delta k. So my point coordinates are the inverse of this matrix kk. And again, this is the block diagonal matrix, which are already computed. So there's no extra effort in here. And this is the hk block minus nkt times delta t. And this is kind of the known parameter that I solved before. So in the second step, I can obtain this matrix nk only needing to compute basically vector matrix multiplication in order to solve for this delta k. And I don't need to do any inversion because this element I already inverted before, and I was able to do that inversion in linear time in the number of points that I have. And so I can also do this efficiently. So what has happened now is that I was able, by design, so how I set up my matrices, to separate these matrices in two blocks, into the orientation parameters of the camera, and before that, the 3D point coordinates. And based on this structure, I could see how the matrices Cij and Bij have been designed based on the Jacobians, which are sparse. This has led me to a normal equation system, which is sparse. And then I could do this trick by multiplying this normal equation system from the left-hand side with this magic matrix, which turned it into a problem that I could easily split up into two parts. First, solving for the camera orientation parameters, and then second, solving for the point coordinates. And all that exploiting the sparsity of those systems. And this is a trick that I'm doing in order to solve this, in theory, very large system in an efficient manner. So, also further note, again, the full Jacobian or coefficient matrix A doesn't need to be constructed explicitly, so you will typically not compute A explicitly. What you will do is you just only compute the elements which are non-zero, which you need, and you are even not computing often A explicitly. You can directly compute the elements of your N matrix, so of your normal equation matrix, just through those low-dimensional matrices. Again, these are these 2x3 blocks. These are 2x3 and 2x6 blocks. So these are all small low-dimensional matrix multiplications that I need to compute in order to fill the individual blocks of my N matrix. And so this can be all done in an efficient manner. And then you construct your reduced system in this form. For that, again, you need to invert nkk, but this can be done in linear time in the number of points that you have, because it's a block diagonal matrix. And finally, you solve this. You construct the system, you solve it with a sparse solver, and then finally can obtain the point coordinates from that. That is a way how you solve your system of linear equations in the context of the bundle adjustment problem, and how you can solve even systems which on the first glance are too large to be solved in a reasonable amount of time. So the second thing I want to briefly look into, and what happens if we actually apply the bundle adjustment problem without control points, because that's also something which we need to take into account, or which can happen if we don't have fixed control points and we need to compute our bundle adjustment problem. But note that in this case, the bundle adjustment problem will not generate you with, only will give you a photogrammetric model, and not a model where the scale information is available, and you have so everything is defined only up to a similarity transform, so a rigid body transform and a scale parameter. And that's something that we have seen already before. This is something where we have used, for example, the absolute orientation problem in order to compute the absolute orientation for a solution that was computed for orienting a photogrammetric model, kind of anchoring it in the real world. And what we now need to think is, consider that we know that if we don't have any control points, the solution is only defined up to a similarity transform. Will this lead to actually problems, numerical problems for us? And it turns out, yes, this will actually be the case. The problem that we will have is that this matrix N will have a rank deficiency, a 7-dimensional rank deficiency, because it has a solution space that can be obtained by using the same photogrammetric model and basically moving it everywhere in the world and scaling it up and down. It will always be the same solution. So we have a so-called gauge freedom, and that means we need to specify a datum. We need to specify this 7 degrees of freedom, constrain the matrix, so that we kind of get rid of this rank deficiency, because otherwise our solver will most likely report an error to us, and then we don't know what to do, right? So how can we change our problem in order to fix a datum, to specify a datum? And we can do this via introducing additional constraints. So what we can do is we can say, okay, the center of mass of my problem should not change. So basically, I'm constraining the center of mass so that it doesn't move. I can also set a certain point as kind of as my 0, 0 point, which shouldn't move. That's also an alternative that I can do. I can also say that the main directions shouldn't change. So if I compute basically the cross-covariance matrix over all points and compute the eigenvectors for this, you kind of want to keep these eigenvectors in the same directions. And you can also say that the average distance between the points in the center of mass shouldn't change. You're basically fixing the scale, that the scale shouldn't change. So if you see this as the points that you have, you can compute the center of mass that you have of those points and say, I want to fix this center of mass. And then you can say, based on the distribution of the points, you want to define your coordinate system. Let's say whatever the first one is, the axis with the largest eigenvector, and then with the largest eigenvalue corresponding to the eigenvector, and you take the eigenvector as your coordinate system. This is, for example, one way. And then you look to the spread of the points in order to fix your scale. So this is one constraint that you can set in order to fix this 7 degrees of freedom by introducing 7 constraints. The scale shouldn't change, the center of mass shouldn't change, and the orientation of the main spread in your 3 points should not change. That's one way for fixing this. There are other ways that you could do. For example, if you can set one of the points as the center of your coordinate system and then maybe use some other points nearby in order to specify where the main directions are in order to fix the scale. You can do this also with other constraints, but you basically do this with a constraint matrix. And so you add a constraint matrix which should fulfill the constraint h times x should be 0. And then this Jacobian, the corresponding Jacobian is actually added to the normal equation system in order to perform this minimization. So you're adding additional constraints which basically fix your gauge freedom. And you need to do this because otherwise you will have a rank deficiency and then cannot come up with the unique solution of your linear system. And so you want to have that and therefore fix your gauge freedom. Kind of the first remark that I want to do at that point. I also have a short second remark. We already discussed outliers and how to deal with outliers in the first part of the bundle adjustment lecture. So far we have assumed everything is outlier free and we were still living in our kind of Gaussian world that we only have the remaining points which are outlier free, are subject to Gaussian noise, and then can compute our statistically optimal solution. In practice, we are doing a couple of steps before in order to get rid of those outliers, or at least reduce the possibility that they are outliers in our data set by breaking down to small blocks, solving them separately, and using other outlier rejection techniques, which I briefly mentioned before. What we, however, since we ever do not know if we actually really found all the outliers in there, what we typically do, we also add a robust kernel to our state estimation problem. That means we are moving away from the parabola that would be the correspondence or the log likelihood, stems from the log likelihood of the Gaussian distribution, and change this distribution so that we have a different shape. And so what we basically do, we want to have an increase in the values further away for large error values, so that it's not a parabola anymore, but a function which grows more slowly than a parabola or even goes up to a constant. And there are different ways how we can kind of reduce this penalty for terms with larger errors if we far away from 0. L1 norm is one example. Everything turns into a linear function. Huber is a very popular choice, which has a parabola close to the 0 error configuration and then turns into a linear function afterwards increasing, or even the more extreme kernel which maintains a parabola here in the middle and then goes basically constant values, so that if you have points which are outliers which are far away than a few sigma, then you actually reduce the impact of this value to 0. And what typically happens in bundle adjustment, you either fix on one of those robust kernels, but the problem is if you really weigh down the effect of outliers which are further away, it always means that you have a good initial guess, because if your initial guess is very far away from the actual solution, then you will actually end up in this plateau of your error function. And then the Jacobians will not pull your points towards the right solution. So if you have a very good initial guess, you're probably fine with an error function which looks like this. If you have a bad initial guess, you want to stick more to some more conservative kernel function, such as a Huber kernel. So depending on what problem you have and what you know about your problem, you may vary the robust kernels that you're using, or maybe even vary those robust kernels over the iterations of your bundle adjustment problem. One of the nice things, there's even a formulation for a robust kernel, which is a family of parameters, so that you have your error function or your kernel function where you put in your error, an alpha and a C parameter. Basically, the C parameter specifies the width over here, and the alpha parameter specifies which function you're choosing. And as a result of this, so for you're basically getting up different kernels. So if alpha is 2, you basically have your Gaussian function over here, and as you decrease alpha from 2 down up to minus infinity, so this would be the value for minus infinity, you obtain different kernels. So you can also use one of those techniques in order to weigh down the effect of errors and even kind of change this during the optimization process. What does it change? So you can show that if you introduce such a robust kernel, then this is equivalent to adding an additional weight term to your points. So you're adding additional weights, and the weights depend on the actual current error configuration. And this is the weight function that you obtain for the different kernels. So this is a weight of 1, which holds for the Gaussian, so everything is Gaussian. Then we have our standard problem, every point is weighted with 1, so everything is identical. But if you choose other kernels, whatever, this I think is the Huber kernel over here, the green one, then you would get a weighting factor which looks like this. So if you go further away from your zero error configuration, the impact or the effect of this point will be reduced through this additional weight. And so you can use those robust kernels and embed them as weights in a weighted least squares problem. And that's how it is done in general. So you will always have a robust kernel running in the background, or to make sure you're not screwing up your solution if you missed a few outliers in your outlier ejection scheme that you used initially. Okay, so this brings me to the end of the lecture today, talking about the numerics of the bundle adjustment problem. So what do you need to take into account when you want to solve the bundle adjustment problem? So again, bundle adjustment is a least squares solution to computing the orientation of cameras and the position of 3D points in the world under uncertainty. And we have done this by minimizing the so-called reprojection error. So the error that we can measure by taking the point where we think the point is, mapping it to the camera where we think the camera is, and comparing this estimated location with the actual measurement that we got. So where was that point, the image, in our actual image? And we are trying to find configurations for the 3D points in the world and our camera orientations so that this distance gets minimized, and minimizing the squared error or the sum of squared errors, or squeezed through a robust kernel function. And this, if we do this in the standard least squares setup, this leads for realistic scenarios to a very large linear system that we need to solve. And if we just would use them out of the box without exploiting any properties of these systems, that would get a system which is too large to be solved. So the first key insight that we have, that is the bundle adjustment problem leads to sparse matrices in nearly all setups. So whenever I'm not observing every point in every image, which is typically not the case, then this will actually lead to sparse matrices, sparse matrix A, and as a result of this, a sparse matrix N. And we can then, first thing we need to do is we need to use sparse solvers, so libraries that are optimized for not storing the full matrix and only taking the non-zero elements into account for the inversions, for the multiplications, so that this can be done fast by picking only the correct elements which are non-zero. And this is basically done automatically for you today if you just tell the system that the underlying matrix that you're using is actually a sparse matrix. And the second thing that we need to do is, we can use the estimation problem and split it up into two parts. First, solving for the orientation parameters of the camera by building this reduced normal system, and then in a second step, computing the point parameters, so the 3 locations of the point, given the camera parameters. And we do this in every iteration, and in this way kind of decouple the estimation of the joint values and decouple the estimation of the parameters for the points from the estimation of the camera parameters, which is typically done within the bundle adjustment problem. So with this, I think you know all the kind of main tricks or things that you need to do in order to actually build a solver for your bundle adjustment system. I hope that was useful and kind of completed your knowledge about 3D reconstruction and how to localize a camera and compute a 3D model of the world using the kind of gold standard method today, which is bundle adjustment. Thank you very much for your attention.